In this video, we will look at the idea of removable discontinuities. And removable discontinuities are kind of like a caveat of vertical asymptotes. So let's look at an example of this. Suppose f of x equals x minus 2 divided by x squared minus 4. If we want to look for vertical asymptotes, we've been approaching this by looking for values of x that make the denominator equal to 0. And values of x that make this denominator equal to 0 are negative 2 and positive 2. So we might expect to see vertical asymptotes at x equals negative 2 and x equals 2. But down here I have the graph of this function f, shown in green, and we have a vertical asymptote at x equals negative 2 like we expected, but at x equals 2, we don't have a vertical asymptote. And in fact, it's not even close to looking like we have a vertical asymptote there. So what is going on in this situation? Let's write f in factored form. So our numerator is already factored for us, but x squared minus 4 can be written as x minus 2 divided, or times x plus 2. So what we have is x minus 2 divided by x minus 2 times x plus 2. And so if x is not equal to 2, so if we put in this little note that if x is not equal to 2, if x is not equal to 2, then this expression right here, we can cancel out the x minus 2 and end up with 1 divided by x plus 2. So if we go back to the graph, what we're essentially looking at is the graph of 1 divided by x plus 2, so long as x is not equal to 2. So we're at x equals 2, it looks kind of normal, but if you were to plug this into your graphing calculator, if you graph this original function, and you tried to put your cursor over the graph where x equals 2, you should get an undefined value. There's actually a hole there, and the function f is not defined at x equals 2 because we can't divide by 0. But every other value of x, this function output is just equal to 1 divided by x plus 2. And therefore we call this x equals 2, that value of x, a removable discontinuity of this function. So a removable discontinuity is a value of x that makes our denominator equal to 0, but also makes our numerator equal to 0, and we don't have a vertical asymptote there. So it's kind of a complicated idea, but essentially it's a place where we expect to see a vertical asymptote, but we don't because that value of x also makes our numerator equal to 0. When considering vertical asymptotes for rational functions, we have to be careful that the x value that we find, where the denominator is equal to 0, does not also make our numerator equal to 0. And this is kind of complicated, so one easy way to combat this issue is to just graph the rational function anytime you have one and visually inspect whether or not we have vertical asymptotes at the places we expect to see the vertical asymptotes. So if you find some values of x that you expect to see vertical asymptotes, you can graph those and see if there is actually a vertical asymptote at those values. And if there's not a vertical asymptote at that value, then what you have is a removable discontinuity.